Okay.
Um, Hi, and welcome everybody from any time zone that you are joining the webinar. Hope you are having good time. Today we are having a joint webinar on the topic of transformative application. We are hosting two speakers, experts in the application of AI in technology creation. Before we start, we have invited President of Eco Science Foundation, Professor Tayebi, to have a welcoming word. And after that, I invite the speakers, Professor Moradi and Mr. Usman, to give us some insight about the transformative application of AI. Thank you. If you allow us, we would like to ask Professor Tayebi, President of EcoScience Foundation, to open the session.
Okay, thank you, Dr. Fatime, and I would like to thank for your cooperation as well as YSF in this respect. And as you know, we have had in touch and in communication to each other for launching collaborations in different ways, in different avenues, and the main goal of such collaboration is to promote and to make more capacity in this respect in terms of young generation for science education in this respect. So this type of event as a webinar on AI, as you mentioned already, is actually related to such objective. I would like to thank you to all participants, especially to thanks to Dr. Hadi Moradi, who is a professor of artificial intelligence at the University of Tehran. And also we have Mr. Mohammed Usman, who is a Ph.D. scholar at the University of Science and Technology in China, technology of China, Hefei in China. As everybody knows, AI, artificial intelligence, right now is playing an important role in our whole life. AI has the potential to enhance the field of psychology and cognitive skilling, which is one of your topics for discussion. Of course, making processes more efficient, personalized, and accessible. So, nonetheless, it is important to address ethical considerations and ensure that these technologies are used responsibly. So, Professor Hadi Moradi would talk and discuss about this very important subject today, and with many thanks to him. In addition, I would like to also mention to real-time analysis that's powered again by AI, which is driving innovations across many fields, offering enhanced efficiencies, accuracy, and responsiveness. As technology continues to evolve, these applications will likely become even more integral to daily operations and decision-making processes again. So I think in this respect, Mr. Mohammed Usman will talk, and many thanks him to him, will talk about such important subject. Once again, I express my sincere thanks to all participants, to especially to the Jamili Foundation and also to YSF as organized this important webinar for today. Thank you.
Thank you, Professor Tayebi, President of Ecoscience Foundation. We would like to invite Professor Moradi to give us some insight how they are employing AI to aid the scientists in screening of cognitive disorders or neurological disease. Professor Moradi, please let us to hear your experience on this subject through your talk. After your talk, we will invite Mr. Osman, and at the end of the session, we have a Q&A time, and we ask the audience to bring up their questions. Professor Maradi? At the beginning of the session, there was a technical issue, and we figured it out that it is already resolved. And I asked my colleague to contact Professor to make sure that the technical issue is resolved. If you let us, we would switch the time slot of the speakers till the technical issue of the first invited speaker is resolved. And for this reason, I would like to ask Mr. Mohammed Osman from University of Hefei to start his talk on the subject of real-time monitoring and analysis of real-time data using AI.
Are you able to see my screen, please?
Yes, yes. And if you could have it in a slideshow, yes, that's great. So we are
Okay.
hearing.
So can we
Thank you.
start now? Let me check the time. Okay,
Yes.
so yeah, everybody, we welcome you all here. My name is Mohammed Usman, and I'm a PhD scholar here at UBRI Lab at University of Science and Technology, USDC, China. And my topic for today is transforming AI real-time analysis for cutting-edge applications. So let us start the topic. Here's the outline of this discussion. We will discuss conventional data mining first, and we will see how data streams have emerged. And since there are many topics within the data mining paradigm, we don't have enough time, so we will be like discussing only the classification problem and a few contributions that our lab has done in this regard, and we will discuss some future challenges as well. So as the first thing that we discuss here is the fact that in the last 30 years or so, we have seen lots of data around us. And since then, the data is like increasing day by day. For example, we have Amazon, Alibaba, eBay, JD.com. These are some of the financial and e-commerce sources that we see around us. And we have some IoT setups, which were initially single sensor based setups. But now they are being interconnected, and we see these setups everywhere. And apart from that, we have social media tools like Twitter, WeChat, and Instagram. We see that millions of tweets or stories or chats are being occurred on the daily basis. And apart from this, we have some other multimedia content apps and applications or websites like YouTube, Netflix. So, what comes in mind when we have this much data? The first thing that comes in the mind is to store this data, and the second is to analyze this data. So human body or human beings are like unable to, they don't have capacity to gain insights of this huge amount of data. That is why we need tool. And for big data analysis, data mining has been around for a while. And it was first talked about data mining was in 1989, where they discussed knowledge discovery from big data. And it was to find some hidden interesting patterns from the data in IJCAI conference held in 1989. Since then, we can see that there have been like many developments around us, and many journals or conferences have been publishing data mining research. In 2000 initial years, we have seen that many businesses have started using data mining in their setups. And we have seen that Hadoop, which is used by Yahoo and Amazon, or Spark, it is used by Alibaba and Twitter. These two big data analysis tools are around these days. So, what data mining can do for us is these are very basic things that data mining can do. One thing is that we can classify the data, we can cluster the data, and we can mine patterns from the data. So when we talk about classification, it is to like it's kind of regression that we do predictions from the data. We will discuss this in more detail, but you can think about it like a spam email classification, or maybe predicting rain from weather data, or predicting the disease patients in some patients database. And we have got many popular algorithms to conduct classification. For example, we have sport vector machines, we have decision trees, we have naive-Bayes algorithms. And clustering is the second part, which is unsupervised learning. I will discuss a little more about supervised and unsupervised learning. In unsupervised learning, we do not have access to labeled data, and we do not have classes in which we can group things. For example, if we want to group customers based on purchase behavior, but we do not need to have any access to labels, and we can cluster the documents based on the contents. And for this purpose, we have k-means clustering or agglomerative hierarchical clustering. The third thing that we can do from data mining is to mine patterns or find we can say find interesting information, interesting rules from the databases. For example, if a customer buys, they are likely to buy butter as well. And for this purpose, there are famous algorithms like a priori or FP growth. From these three things, we are going to concentrate on classification problem. This is one of the classic weather example that we have seen in data mining books a lot. And you can see the data on the right hand side. We can see that we have outlook, temperature, humidity, and wind information. Maybe we can have temperature in Celsius degrees as well. And we have a decision label at the end of the data. We see that plays off or on. So in this case, we are going to read this data, and then we are going to predict. So the steps here are like, first of all, we will um, uh, take out a chunk of data. For example, we take out 80% of the data and send it to our model. It will train itself, and from the training we are like going to build rules. For example, if the outlook is sunny and weather is hot, and we have humidity and there is no wind, then there will not be a play. So in this case, it is going to create lots of rules. uh, an algorithm will create lots of rules, and it will basically train itself, and it depends upon the inner mechanism of an algorithm, how it trains itself. So for 70 or 80% of the data, we are going to train the model, and then for the 30% or 20% of the data, we are going to test its performance. And at the end of this process, we are going to say that, our model can like predict the weather uh, up to 80% accuracy. In other words, our model is 80% or 90% accurate. So if you provide it with outlook, temperature, humidity, and windy, then whatever information or whatever decision it makes, it will be 80% correct. So this is the classification problem, and it is supervised. By supervised, we mean that we have got historical data with us, and we can like train the model from that historical data, and it has got labels as well. By labels, I mean the last column that we have seen here. We have play column here. You can see on the far right of the first picture that we have on this slide. So next, we will discuss about data streams which are around us these days. And this kind of data was not present in the like data generation, I would say, we have seen in the 1990s or so. This kind of data is like very advanced, and it is real time, and it flows continuously. There is like no gap in it. The arrival time may be regular or irregular, but it arrives continuously, and it is evolutionary as well. From evolution, we mean that it could change its distribution. For example, we have web logs, we have credit card transactions, we have weather data, we have stock trading data or sensors data. And the mining of data streams, that is the real world data, real time data, uh, is somewhat very similar to what we have in data mining. We can do classification, we can do clustering, we can extract patterns from the data. And from all this, we are going to discuss supervised classification, which can be used for disease diagnosis. For example, we can use it for network fault detection or spam filtering or financial fraud detection. A small historical chart has been given at the bottom of the screen. We have seen that early developments of online algorithms was started in 1990s, and from there we have seen many developments. A major project was launched as a Stream by Stanford Stream Data Manager project in initial years of 2000 decade. And we have seen a big data stream mining tool, massive online analysis, MOA framework. It is Java based tool. It was proposed in 2003, and it is widely being used these days as well. And one of the major developments is Apache Flink and Apache Kafka. I have not given it here, but Apache Flink and Apache Kafka are being used in many major real-time applications these days. And there have been many developments in real-time analysis. So this kind of data has certain attributes. For example, it has a continuous nature. It like flows continuously. It The arrival time of the instances might be irregular or irregular. For example, It can have one batch at 30 seconds. The next batch might arrive at 1 minute time interval. And it has certain speed as well. And it has evolving patterns. We will discuss about evolving patterns in detail because it is very much linked to classification problem. From evolving patterns, you can think it about like changes in the data distribution or changes in the data that arrives at particular time intervals. It can change. And it will affect our models as well. And the point is known the reproducibility. In the models that we have seen previously in conventional data mining, those models can be trained in offline fashion. When we say offline fashion, then we will give it the whole data at once. In case of data streams, the whole data is not available. It drives instance by instance, sample by sample, or batch by batch. So we do not have access to everything at all. So what we have is partial view of the data. So that is very difficult to learn. And in particular, we are going to talk about data stream classification problem. And for example, we need to suggest a product of interest to a customer in an online store, or maybe we need to classify spam emails in an incoming email system, or maybe find network faults, or detect a credit card fraud. And for learning models, we have online models, batch-based or hybrid models. In online learning models, only one sample is processed at one time. Batch-based may have multiple like instances, and we have sequential evaluation strategy in these models. I will discuss about it in the next few slides. So what are the real-time applications of data stream classification? We can see that this is a healthcare system, and we have lots of sensors which are reporting about a certain patient. For example, there is a heart rate monitoring sensor, there is a wearable device. It can also report many statistics and blood pressure sensors. So these kind of data are being stored in an IoT cloud. From IoT cloud, you can think it like a data storage that is receiving data from multiple patients, and it has historical information of like many patients, and against certain diseases it has a label that whether a patient has this disease or not. And once we need to like declare a patient as a disease patient against against a specific disease, then we are going to build a model from the previous records. And we are then going to like analyze this patient's record and match it or predict it with the model that we have built from the historical data. This is one of the examples, and maybe we can use one data of one sensor, or maybe of multiple sensors as well. This is agriculture 4.0, smart agriculture we call it. This was launched in, I think, 2019. And we can see that there are many sensors which are being used in this data. If we talk about weather sensors, that we have already seen that we can collect the data of temperature, humidity, wind speed, and rain, and then we can predict rainfall, or maybe some other decisions could be made using this data. But for that, we are going to collect historical information and then build our models. So there are two basic fundamental issues or challenges when we talk about data stream classification. And these are a little bit technical. I'm not sure about the ability of participants today about the technical understanding of this particular challenge, but I will try to make it very simple. So these are concept drifts which occur in the data from time to time. I have told you that in data streams or real-time systems, the data does not arrive as a whole. It arrives from like sample to sample. So if there are changes in the customer behavior based upon time or based upon some season, that you are not able to recognize that pattern. For example, if a customer is buying a certain product in summer season, and the same and you are going to suggest him or her certain variations or certain other products based upon his likings, based upon season his interest changes. And if you do not learn that behavior or do not learn that change that has occurred in the customer's behavior, then you are going to suggest the same products as you were like suggesting it in the previous season. This is called concept drift. For example, there is a like a spam email system. You might have received many spam emails in the past, and the spammers actually they adopt different ways to like hit your email box. And for that purpose they change the email contents. If you have built a model that detects the changes in the email contents, and on the other end the spammer changes their email contents from time to time, if your model does not adopt to those changes, then they are going to like classifies those emails as legitimate emails instead of spam emails. So these concept drifts are actually the changes in the data distribution, and their arrival or their occurrence is either abrupt or it could be gradual. If a concept changes suddenly, then we call it as abrupt drift, or if it changes like very slowly in a very progressive fashion, then we call it as gradual. And some drifts occur in a repeated fashion, they reoccur. So this is called recurring concept drift. And you can see the performance of some algorithms on this screen on the right hand side. We see that many algorithms suffer from the like lack of classification performance. And first right hand side, first screen, first figure shows that there is an abrupt drift that occurs at 100 stream step. And we can see that the classification performance of many algorithms goes down. They were performing very well before this particular time interval. And on the bottom, we see that a gradual drift has occurred, and most of the algorithms do not recover well from the gradual drifts. And some of the algorithms which are proposed for data stream classification are like detecting the concept drift. They monitor the performance of the algorithms, their own performance, and then they decide if the performance is going down, then they restart the learning procedure. And sometimes the algorithms do not use explicit detection. They just reset themselves at specific intervals. And in all this, the major issue is gradual drifts, because they are very hard to spot, and at a certain period of time there might be two concepts partially active, and it will be hard for the classifier to detect that which concept is evolving right now. And as far as the literature on this topic is concerned, recurring concept drift, there is not a lot of work that has been done. And the second problem that we face in such real-time systems is class imbalance. And with particular reference to class imbalance problem, on the right-hand side, we see that one class has very small presence, and the other class, that is the red class, and the blue class is very large in numbers. So this is a particular class imbalance problem. You can think it like a patient's database. The disease patients are small in numbers, and the well beings are like large in numbers. And then on the right hand side, first figure, figure B, it tells that sometimes the class imbalance problem could be seen like there are very small clusters within the data that make the classification problem very complex. And sometimes there is a like class overlap, the figure C, we can see that some instances of red class have very much similar attributes to that of the blue class, so they are hard to predict. So these are two problems that are making the classification problem more complex. And nowadays there is a discussion on another issue that we have not seen in real-time analysis a lot. This problem has been addressed in many uh, offline systems, and in real-time analysis, this problem has not been addressed a lot. This is the existence of missing information in imbalance scenarios. So you can see these starred numbers, these starred samples. If you remove these samples, the minority data would become very small. And if we have like this condition and we have missing data, then these two big clusters will form very small clusters on right hand side. And if we remove the samples with missing information at the boundary area, then this boundary line may become invalid. In other words, if you are going to remove missing information from the data, then you are making the problem more complex. So there is a need to handle this issue by like imputing the information instead of removing the instances with the missing information. These are few more challenges that has been like identified in a recent paper that I have cited below. Uh, but I will talk about a solution that has been designed for this purpose because we do not have much time. Actually, these two problems that I have discussed may co-occur, and this co-occurrence is like very important to resolve. And we have seen many methods which were initially proposed for concept drifts or class imbalance problem. And nowadays there is a trend to like handle both of these issues together at the bottom of the screen. This is some of the list of some of the methods which are proposed very recently from 2018 onwards majorly. And more recently, we have seen more papers coming on this topic. And from these topics, we are going to discuss some contribution that our lab has done, and we have proposed few methods for real-time at USTC. And from these methods, I am going to discuss the Emerald ensemble method based on reinforcement learning for imbalance and drifting data streams. This method is actually focused on very high imbalance scenarios, and it is aimed at resolving the imbalance complexity, and then it uses reinforcement learning framework to like manage the ensemble pool. These are very technical terms, but I'm going to try and explain these to you. So first is min plus plus. This is a data level component, and it actually does what could be seen at the bottom of the screen. It will be very easy for you to understand what it does. You can see these small little clusters at the first screen. The first step is to enlarge these clusters. This first figure turns into the second one. You can see the size of the clusters is improved. What we do is we create similar samples within each cluster and make their size bigger. At the next step, if there is a class overlap, for example, we have a black area, this rectangle, there are kind of mixed area where you cannot recognize which sample is what. Then we are going to clear this area by undersampling. The first step is to perform oversampling, that is to generate synthetic instances for the minority data. The second step is to undersample the majority data to clear this area, to clear like the area where overlapping is there. So if you have the third scheme, if you have, for example, this kind of situation, the figure number 5, if you are unable to see my mouse moving, then you will see that this uh, situation becomes very clear in the last screen. The clusters are like enlarged, and we have a clear boundary area. And this is very easy for classifiers to learn from. And since the minority samples may become very scarce at times, for example, at a certain batch, we do not have a lot of samples. We have designed a storage to store these samples, and we have use a life factor and a weighted ensemble recall to like mix them up to create a score. And then we, for example, we have these samples stored with us. Then the life is given by this column. It is decayed at every batch, and this is weighted recall as well. So we use both of these to decide whether to like remove these samples from the queue and keep the new ones in. And then we use reinforcement learning in order to manage the ensemble pool. We train the agent, and it will keep records of the classifiers in the ensemble pool, uh, which are kept in the pool from time to time, and decide which ones to like use for building the ensemble model for the prediction purpose. This is very technical, so I think I can skip this. And this is the learning framework. It is very much different from what we have seen from conventional data mining. You will see that we have a batch preparation at the first stage, and prediction is done for as a first task, and the scores are calculated. This is done using the available ensemble model. But side by sides, whenever a batch is ready, the model is updated continuously on the right hand side. For example, you will wait for like 50 samples together, and then you will update your model based upon what you have seen in the data. So this is real-time ensemble modeling, we can say. It is conducted at batch level. The experiments were conducted in this study on 104 data streams. And you can see that there is a variety of data streams that were created. And the right hand side shows a study that was conducted before this particular paper that I am uh, trying to explain. And this paper has actually shown that how the analysis could be done for this type of work. You can see the performance of many algorithms here on this screen, and the darker performance shows better performance. For example, for our proposed method, Emerald, we can see lots of green shades at the bottom. Some of the methods, you can see that there are white, more white. Then we have this second part of the data sets. This is recall performance against the minority class. We can see that most of the methods suffer from the low performance. You can see some white area in which we have like lots of low performances. This is rare type of data. And again, this area. So this is like kind of future work that can be done in this domain. This is the performance against increasing imbalance ratios, performance on dynamic IR, and moving, merging, and splitting clusters. This is on rare minority instances. We can see that low performances are very much in there for the rare data. And this is overall comparisons. It is Nevenji statistical comparison on the
Mr. Usman, we are not hearing your voice. Are you disconnected? Sorry, it seems that Mr. Muhammad Usman have some problem with the system, and our colleague he tried to help him to get connected. Um,
I think he's disconnected. I asked Bilal to try to get him back to.
Yeah, Mr.
um,
Usman is coming back. He's joining back. I just
Yeah,
contacted him.
okay, okay.
Okay. Are you able to hear me?
Yes, we can
Yes,
hear
we
you.
do.
Please share your screen.
Okay. Okay. I have turned it on already, I think. Give me a second. I will share it again. Can you see it now?
Yes. Please turn it in
Okay.
the presentation mode.
Yes. Sorry for the interruption. I had some internet issue. Can we continue?
Sure, sure.
Okay, so the Emerald uh, ranks at first in first case, and in second case, UOB is another algorithm that ranks at first, and we have Smart OB ranking at first in another scenario. As a whole, we see that Emerald performs better than other algorithms on more than 100 data streams. So, according to our contributions, I have not given any details on the other two, three algorithms that we have proposed, but we have seen that addressing imbalance complexity improves the performance. We also see that adaptive minority storage is important for learning in real-time scenarios, and we need to have imputation strategies in order to deal with the missing data. And some more work can be done on in future, and some of these points are to make the parameters more adaptive of the current algorithms. Maybe we can add feature selection later on, and for rare minority instances that sit very deep into the majority areas, those are very hard to detect. So this is a potential future work. Recurrent concepts are another problem that has not been focused a lot, and obviously the multi-class classification problem. uh, these are some of the works that have been done in this regard, and you can check my more work if you can scan this QR code. So that's it from my side. If there are any questions, we can address those at the end, I guess, after the second talk.
Thank you, Mr. Muhammad Osman. If you let us, we keep the question answer session for the end of the webinar. And thank you for describing the principles and applications. And we would like to ask Professor Moradi. Thank you, Professor. We are seeing your slides.
Do you have my
And
slides?
if you put it in slideshow, great.
Is it ready?
Yeah, but
Okay.
that would be great if your voice would level up a little bit.
A little bit developing. I'm trying to talk louder, if it's okay. Thanks, Mohammed. That was great, and it was making my life a little bit easier describing the machine learning concepts. Okay, what I'm gonna do is more into our application of AI and machine learning in psychology or cognitive screening. Maybe call it computational psychology or computational psychiatry. You know this guy, and you may say, "Oh, wow, that's a great guy, Einstein." But it turns out that he was diagnosed with autism. And another one, we have Isaac Newton, that he was also, he had kind of symptoms of autism. He was going to a classroom without any students. If there is no student, still he was doing his teaching. And let's look at another one, Darwin. And the same thing happened with Darwin, because he was a great scientist, and we have always talked about his evolutionary theory. And the point was that he had difficulty communicating with other people using just face-to-face communication. He used to write it. And if we go further, we have Thomas Jefferson, the third president of the US. When he wanted to go to a meetings, important meetings, he had a mockingbird on his shoulder and he was in pajamas. That's a sort of behavior of the children with autism or people with autism. They in the kind of hard situation, they behave in a specific manner. Now, let's just simply I show a little bit of issue a person with autism has. This clip has been created by the autism organization in the in the UK. And you can see it's a sort of a view of a person with autism, that the things that are very simple for us, it's very focused and highlighted for this type of children. And the sound of special sounds, small sounds, it makes them kind of unhappy, and it's a sort of huge noise for them. And the point is that many times we may see such people in the environment. You see that the sound, the smell, the color, the lights, they make them kind of unhappy and uncomfortable. And you can see that the mother tries to comfort the child, and still it has difficulty. At a certain point, he cannot tolerate it anymore, and his behavior becomes sort of unconventional. It's not regular to other people. So that's sort of one of the issues with kind of psychology that we have. Now, if you look at this one, the question comes is, what's the relation between engineering and psychology? It's a barrier between these two areas, and I'm trying to get into it. Let's look at another pattern of children with autism. You see this little guy, he just constantly putting things together in a specific manner, adjusts them, and it falls, and he does it again. For how many times? It does it for half an hour, or even more. He likes to put things together one after the other. And at the same time, if you look at this things that I have written on the right side, you see, if I ask you, what do you see? You look at it, most probably you say, I see an A. At the same time, it's an H. But a person with Parkinson's says H. It doesn't see the whole thing. It doesn't see the A, the design of A. So that's the point. That's okay. We have some sort of problem like autism. What can we do? One point is the same way that Muhammad explained. You see that these are the distribution of, say, the blue ones are the people with Parkinson, and the red one with, I'm sorry, with autism, and the red one are the normal one. If you try to separate these, it's kind of difficult. But if you use a mapping into a new environment, as you can see, the blue ones are on the right side, the red ones on the left side, a little bit of overlap exists, but there are a small number of items or samples are like that. So you can easily draw a line in here and say, oh, That's it. I came up with a solution and with the separation or classification. So basically, we can find a line here. So that's the point. So what can we do with this? How can we get the data? Muhammad talked about a lot of data coming in, how to deal with them. One of the things is, as an engineer, we have done this one. We looked at the symptoms of autism and look at it, okay, what happens is this children, what problem that they have is they, as I mentioned, they focus on the small points in the environment. They look at very tiny things. So what we did is we put an accelerometer in a car, and also we try to put a shaft encoder on the wheels of this car. And as you can see, what happens here, we could collect the acceleration that made by the child that you see on the lower right lower side of the screen, that the child playing with this toy. And it was interesting to see that we tried to come up with, from this acceleration items that we have in three axes, X, Y, and Z, we try to come out what's the difference between children with autism and normal children. So it comes to the point that AI comes into the picture, and if you have a huge number of features, what features are the more important ones, and what are the basic aspects on that feature? And what happened was that we saw that these children, interestingly, there is a feature that you cannot find in a textbook, that the children with autism didn't push the car, but the normal children tend to push the car. And the first thing comes to the mind, that is it a valid feature, is it a good one? And as that data that we had and AI aspect of it, it was correct. And we talked to the experts. They said they started to thinking, what's the meaning of it? Why a child may push it, a normal child, and a child with autism don't push this car. So after so many collaboration and discussion, it came out most probably children with autism, they don't tend to explore. They don't want to get out of their comfort zone. So that's the reason they don't push the car to see what happens. But normal children try to explore and they push the car. That we try to see, we saw that the children with autism, they have difficulty working with other people and interaction with other people. So what we did is we built a robot to see what's the difference between disparate type, the interaction of the child with autism with disparate type. And we try to see what happens when I just go forward to see, show it faster. These are the normal children. As you can see, they tend to create new environment. They tend to interact with this robot and ask them questions and try to play with him. And we did the same thing with children with autism. And it came out that there are many differences between normal children and children with autism when they try to play with this robot. And that came out with a sort of way to screen or pre-screen these children. Now, I mentioned these samples because I want to point out that when you want to do the same thing, similar thing, you have to study the symptoms that children with autism or children with ADHD or children with other cognitive deficit has. You see, shaking hands and moving their parts of their body, especially their hands, and flapping is sort of typical approach by these children. So based on that, we came out with the idea. This is kind of old idea, and it's based on the Kinect. And in the okay, and Kinect, you may have played with Xbox. That you can just move around on the front of Xbox, and it detects your body and your skeleton, and based on that you can play a game. we use this system and we try to, first of all, as you can see, detect the structure or the skeleton of the person. We hide their face because we don't want to be shown by other people to other people. So based on that, there are many points as on the skeleton that you can see these repetitive behaviors of the children with autism. You can detect it. So that's the portal. We did it, and one of the things that these children have is tiptoe walking on their fingers, on the tiptoes. And that's what was one thing that by getting this skeleton structure through Microsoft Kinect, we could use machine learning approaches to screen these children. So again, let me go back to the idea that this type of deficits is all over the world and people have it. You may see that, for instance, Satoshi Tajiri, the one who came with Pokemon idea, he was the sort of Asperger or high function autism. So having a sort of deficit doesn't mean you cannot be successful. You can be successful, but there's something that you better to work on it and solve it. As Mohammed mentioned, I'm just giving out for the people who may not be familiar with machine learning. The point is, if you have a bunch of samples, in this case, these are the samples as you can see as a circle I have here. The question is, can I just fit a line on it, or this curve on it, or this one, or this one? Which one is the most or the best hypothesis to match this number of samples? That's the job that machine learning is going to do that, and for the pattern that we want to learn it. So just let's get a little bit further on the cognitive issues that I mentioned. As you can see, this is ADHD statistic in the US, and you can see that it's huge. It's huge between 4 to 17 years old. And the point is, it costs a lot. It's $14,576 per year for each person, and it's for the Americans over $40 billion. That's for the Parkinson. For the ADHD. Now let's look at the autism. Autism started, the numbers that we have is 2004, it was 1 out of 166. Before that, it was 1 out of 1,000. And you can see that it goes high and high. It's up to 2018, that figure shows, but currently it's around 1 to 39. So you can see that there are many people have symptoms of autism, and it needs to be detected and at the same time to be handled. So let's look at another one. I talked about children, but it doesn't only limited to the children. You can see that Alzheimer, it happens for the elderly, and there are many of those around. And you can see that it's 5.5 million or 10% of the people over 65 years old in the US. I use the US because it has many statistics that you can easily use and get it online. And by 2050, it's going to be 16 million. It's going to triple time, because the number of elderly is going to increase. And you can see by 2050, it's going to be what $1 trillion worth of budget that they have to spend on this problem, on this issue. Now, let me go back to the screening methods that you can or we did it, and you can do the same thing. You look at this game that it's a hand-eye coordination game. You have to, the child has to grab this bee and move it around these flowers. In this case, it's only a line, to grab this and go to his cage or to his home. And as you can see, we have drawn these paths in different directions. These have taken from hand-eye coordination test called Frostic. So you can look at the psychology, get similar or something similar to that one in the computer sort of format, and then try to collect data. And you can see these different patterns that these are normally have done by the children with autism. And in the yellow ones, the white ones are the ones that the child didn't grab the bee and just moved his finger around the screen. The black one are the ones that he has moved moved the bee alongside the path. And we did it as a game, so children like to do it. This was the first level, easy level, which is a straight line. Then we came up with one curve, then we came with multiple curve, and then it's much more difficult patterns. And it was interesting to see if a child can handle this kind of hand-eye coordination task. And just go back to the initial task and initial sample that I had, you see this is for a normal child, and this one is for an autistic child. And you can easily see the difference. So it comes to the question, how can I use machine learning and AI to differentiate it, which the ones who are familiar with AI, it can be done easily. And you can see here that one of the things that they do is, first of all, we have to visualize, simply visualize data. You see these red ones, these are the autistic children, and the blue ones are the normal ones. This is the score that the person has got during the games, and this is the average curvature of the path that the bee had to move. And with this easy line between these two classes, we can easily separate these and say, okay, if you are below the line, you probably have autism, and if you are above it, no, you don't have it. So let's go back again, just giving this idea that, look, Mozart, famous songwriter, he had autism. He used to jump on the tables and behave like an animal in some cases. So it shows that, again, you can be successful, but you may have some issues that you have to deal with it, and it should be screened. That's the point, that it's about the brain. Everything like these things comes from the brain. It's cognition. From the baby in the mother's belly to the first years, to the teenager times, to something between 16 to 30 years old, to middle age, and finally we get to the elderly. This brain is going to improve and also decline. So the point is, if we can early, for instance, for Parkinson type of thing, or for Alzheimer, that the brain is going to shrink and some of the cognitive deficits is going to show up, we have to do early screening to be able to get ready, to be able to apply intervention and to try to minimize this brain decline. So this part is going to be early screening, and then we are going to report it to the doctor. It's going to be the diagnosis by the doctor, and then finally comes to therapy part. So the question comes in, what's the general approach currently done in psychology that they use this type of screening? It's one approach is a questionnaire that a trained person can do it, and an expert does the face-to-face examination. And finally, there are some tests or biological tests that you can do to make sure that assessment is complete. Considering all these approaches, this data that you see is from the US. They have difficulty to find problems in 40% of elderly in the US. In the dementia case, is about 50% didn't get the diagnosis. So you have a person that has dementia, but at the same time, you cannot detect it. Why? Because the expert doesn't have all the information. The expert doesn't have the complete expertise and needed expertise. And it comes to the picture that even in the US, with the very high medical standards, the complete diagnosis is not done. And the problem is, if we have this kind of deficit and it's not detected, we are going to have more problems in the future. And the problem is that the cognitive problems over time, it gets difficult. Now, one interesting and one good thing that happened in recent years is our mobiles. It's a complete gadget of sensors. You can see that we have tons of sensors as proximity sensor, ambient sensor, GPS sensor, accelerometer, touch sensor, gyroscope, magnetometer, temperature sensor, microphone. And all these sensors can be used, as Hussein Mohammed mentioned, you are going to have a time series of information just coming in, and there is a big data, and you can process it to get information about the brain health and psychological health. One example is that we did was when you try to work with Telegram, with WhatsApp, with ChatGPT, I'm sorry, not with ChatGPT, with TikTok, Instagram, when you look at it, you based on the content, you are going to show emotions. And that emotion is going to be short term, maximum of 30 seconds it's going to last. But the point is, if you're in good mood, you're going to laugh higher. If you're in good mood, if a picture comes with the sad events, it's going to turn you down. And but if you're in a bad mood, a good picture, a funny clip comes in, you're not going to react that much. So basically, if you look at the pattern of emotion of a face, you look at your phone and you're looking at it, and then it's going to tell you, oh, you have a problem. You're not in good mood. And funny is one thing that you can do is, and we have done it in a very short, very small experiment is, I'm going back home and my wife is home and I am looking at my phone and it's going to tell me, oh, you're not in good mood. And at the same time, it says a short message to my wife that, look, your husband is not in good mood, be careful. So that way you can use machine learning, AI, and the gadgets that we have on a mobile phone to be able to detect the mood and help social life of a person to get better. Now, let me shortly go back to, I'll just give you this one as an example of what we can do to go from analyzing a cognitive deficit to get to the point that be able to run an application, run a system to be able to do diagnosis. These are the things that happen in case of Parkinson: tremor, slowness in movement. They have hard time in speaking. They have hard time in showing emotions or understanding emotion. They have hard time in solving problems. They are kind of anxious and they have rigidity. So based on that, one thing that we are currently doing is we have designed a system that look at the face, because the people with Parkinson, they have the masking face. They cannot show the emotions completely. They have their volume of the speech is not going to go up and down that much. And also in emotion recognition, they have problems. So we made this application. And one thing that we did, and most probably everyone has to consider, is when you try to work on one of the symptoms, you have to do what just understand completely the symptom, because we are from the engineering side and we want to step to medical and psychology side. And then we have to design the task that completely can do that one, which is the handwriting, which controls this tremor in hand. And what are the goals that we have, and then also see what data that we have to collect. And then based on that, if you design it completely, we have to go for the testing. The same thing goes with Alzheimer. I think I have 1 or 2 minutes more. I just skip this one. Another thing that happens is learning disability. And if you look at it, this happens for all the children from the 4 or 5 years old. You can see it and you can diagnose it with dyscalculia, dysgraphia, and dyslexia, which goes to reading. This one example, this is a fish finder game that we designed it. The current approaches that you see is based on the questionnaire, which is parents have to recall and answer the question. They make mistakes. There are questionnaires for the children themselves, but it doesn't measure hyperactivity. Again, EEG caps can be used expensive and limited. You cannot use everywhere. Camera and marker on the head, the same thing. And finally, there are applications that look at the face through the computer, but that has, first of all, one problem is that it's privacy because it takes image. We have to take care of privacy. And the head movement is only the part that it measures. It doesn't measure the hands or other things. But as I mentioned, we have the phone that has accelerometer. And if you look at the left one, this is when we gave the game to a child, a child with ADHD, you can see this is a pattern of accelerometer. And the right one is the pattern for the accelerometer for the normal child. You can easily see that these are different. So basically, we can run simple algorithms that we have designed with machine learning algorithms to be able to classify and distinguish between these two. And you can see this, the top one is the accelerometer for a normal child. And you can see here that the sharpness of the movement that you cannot see in this one, that shows that a child with ADHD has higher acceleration when he's playing with the game. There are other games that we have made. They're just focusing on the brain and on the attention and memory. That's an example. This is called the pattern memory. As you can see, there is a pattern that you have to select it after it's gonna go out. So the yellow honeybees should be selected when the honey hive should be selected when he goes away. So this is a pattern memory. Then you have other task that has been done by for the cognitive selection. This one is we call the rainy clouds. That basically it's a divided attention that you can see the performance of the normal children with the children with, for instance, other deficit, or even when you go and get old, you see if this ability is reduced or not. And this analysis, as you can see in the same thing on the rainy clouds that was focusing on divided attention, you can see that is the performance of normal children, and this is the performance of an ADHD child, a group of ADHD children. And you can see that the difference between these two are significant. It can be easily detected that these two categories are different. So since my time is over, I had some other slides to discuss it, but it doesn't matter. The main part of the idea of how engineering can come to fields like psychology and cognitive sciences to help for screening and also improvement, I have shown the basic ideas. Thanks, Fatima.
Thank you, Professor Moradi, for the exciting topic that you brought up in today's webinar. Now we have some time for discussion on the topic that our speakers from EcoSF and YSF had today. The session is open to all the audience, and we are thankful to the participants in this session, and our speakers are ready to answer your queries.
Dr. Fatemi, you may ask the participants to raise their question through chat box in this respect.
If you have difficulty on using the microphone, you may read your question in the chat box, and I read it aloud for the speakers.
I think, Fatima, there is a question from Sayed Ifrah. Is hyperactive disorder developed in elderly people or not? It's possible. In psychology, something may happen in at later years of life. But hyperactivity normally happens about 3 to 4 years old. but the time for detection or diagnosis about 7 and up. And the time that you have for diagnosis and then intervention, mostly it happens between 7 to 17 years. If passes that time, you have to learn how to deal with it, because after that it's kind of harder to intervene and solve the problem.
Dr. Fatima, may I raise a question from Mr. Usman, if possible?
Yes, sir, please.
Yes. Uh, uh, Thank you, Dr. Mohammed, for your nice presentation. As I understood, regarding, the gradual drift, as you mentioned it in your presentation, there would be a trend within gradual drifts. If am I correct, you can correct me or not. If so, which type of the mode we should consider for this trend? Would be a parametric mode or a non-parametric mode? You can explain.
Okay, in fact, uh, I have talked about gradual drifts, which could be like handled at using implicit approaches, I would say. Implicit approaches then depends upon what kind of models you are building. Sometimes, like in our research, we have built models using ensemble learning. And at times you need to pass on some parameters to ensembles to like restrict them. But these parameters are like very safe. And in explicit detection of drifts, those approaches which are designed for explicit detection, they solely rely on the parameters. So they are strictly parameterized. And implicit adaptation, I would say, that is non-parameterized at times. I hope that it addresses the question you have raised.
Right, right. You're correct. Yeah, I got it. And on the second question from you. So again, if I understand, we can, say would be a model of, AI, artificial intelligence in this respect, able to balance the data classification regarding the missing data, as you mentioned, during such a slide, you mentioned some missing data. I mean, any model of data can, balance such data classification.
I do not understand the question. I do understand that you are talking about missing values, impact of missing values on the classification problems.
Right, yeah, you're right. Actually we face missing values or missing data for a trend, for a phenomenon, everything, just right. So a model of AI should should go ahead to make some maybe predictable or predictable data in this respect to be actual, to be close to
Yes,
actual
yes,
data.
yes, exactly, exactly.
Did you get it? The point? All right.
Yes, yes, I
Oh,
understand that. In fact, the
right.
research that we have published a recent paper which is called bin.ini. It was listed in my publications. And in that paper, we have used linear regression models. And those were
Right.
built specifically for data stream environment. You will understand linear regression models are like in for like many years, and we can use those for prediction tasks. In these cases, I have used linear models to like predict the values of missing columns. building like many models in a repository. I've been storing these models in a large repository and picking them depending upon the situation which is present according to the concept drift. So in that case, I have compared it with mean imputation. Mean imputation is also a strategy in which you take the average of the existing values and then you impute that based upon the average. And when I compare it with the mean imputation, then my performance is much better than that. So that is why I have used linear regression based imputation. So values close to the original values do matter a lot. This is very important question.
Right. And I would like to make a link between your subject, especially for some gradual drift, and Dr. Hadi presentation. You know, if you consider the behavior of autism kid, for example, or Parkinson person, would be you know, again, a drift in this respect to the behavior regarding an autism person or not. Would be a drift, would be a gradual drift under a trend in this respect, and there, you know, a linear, for example, linear trend or non-linear trend in this respect. Maybe may I ask Dr. Moradi to just answer this.
Thanks. Actually, that's a very good point. In the elderly, Alzheimer, Parkinson, and MS, all these type of uh, diseases, they tend to get worse. So one of the things that the doctors like to know is how it progresses through the time. Because, for instance, the person goes to the doctor and today in the clinic and gets his medication and goes home, goes for a month or 2 months, comes back to the doctor, but doctor doesn't know that during this time what happens to him, and they're very interested to know what happens during the time. And that's exactly what Muhammad mentioned, that we have a time series, we have a change in this, and the change is not necessarily linear. It could be exponential, it could get worse very fast. So that's one thing that we can look at it and work on it.
And my last question, you know, you talk about toys and the role of toys, especially to autism, you know, children. So any type of toy, for example, STEM toys, science, technology, engineering toys, can help, you know, to correct the behavior of, you know, an actually autism child in this respect. Would be helpful to use AI, of course, in this respect.
That's a very good point. Yes, the point is the STEM kind of toys like Lego. It has a lot of parts that maybe in the future we would be able to put on them some sort of IoT devices that when you put them together, you can exactly determine where they're located and how they have placed together. One thing that can be done is using the cameras. That if you have a camera over in the daycare center and you look at a child, how he plays with the toy, and or even how he moves around, how he interacts with other children, it can be used exactly to determine if there is a deficit or the child has the normal progression in the daily life to learn things and to be able to interact with other children. The only problem with the cameras and security cameras, in China, they use it a lot, but in other countries, they have the privacy issue. That's the reason using the devices that they have IoT systems in it, it makes it the privacy much more easier issue, and that can be dealt with it easier.
Okay, right. Thank you very much.
You're welcome.
Dr. Fatima, maybe you have some question to raise.
Okay. Her microphone is muted.
Yeah.
Ah,
Yes, I think her mind is not available. She's
yeah,
not available, right? Okay.
yeah.
Yeah.
Okay.
Dr. Fat, so, okay, I should continue moderation of the session. And thank you very much, Dr. Moradi, and thank you very much, Dr. Muhammad Usman. I think this issue and this, such topic is so, interesting to learn about, them. And then hopefully we should continue such, topics in the future, which more applications in different area we can use it. Thank you to you all, to you both presenters, and to all participants. And I would like to thank to my EcoSF team, Mr. Bilal Khalil, and also thanks to Jamili Foundation, YSF, Dr. Fateme Muhammad Pana, Dr. Muadab, and Mrs. Manzumi, and other colleagues at the Jamili Foundation. Thank you very much for your attending and for
Thank-
your participation.
Thanks
Sorry,
for your invitation.
my microphone was not
Thank
activated,
you very much.
and
Thank
I
you.
still get connected from the account. My colleague.
Dr. Fateme, we should say goodbye to. Okay, we say goodbye to all.
Thank you
Have
very
a good
much.
time. Thank you. Thank you very much. Goodbye.
Goodbye.
Goodbye, Dr. Hadi. Goodbye, President ECSF, sir. It was very nice to be here in this presentation. And I have
Nice talking
attended
to you.
few presentations in the past as well, few webinars which were held online, and it is always very informative and is held very regularly. I have seen one more webinar coming in August as well, so I'll be happy to join
Sure,
that as
for
well.
sure.
Dr. Hadi Habib Tayyab is one of my colleagues, and he is working in psychology domain, business psychology. And later on, we could talk about any collaborations that we might do in the future.
Sure, I left my email here that to get in touch, and it would be great if we can work together.
Yes, sure. I have noted it down, and I'll pass it to him, and
Thanks.
we can then discuss it further. Thank you very
Sure.
much, uh, President, and Mr. Bilal. Thank you very much for hosting this session as well.
Thanks, everyone. Have a good day. Bye-bye.